And then when you're trying to model this, and you try and do computer models, the first thing you do when you do an engineering model of something is you assume uniform flow through a channel. Well, there's my uniform flow. That appears to be going vertically upwards. So that's a bit of a problem when you're trying to create a computer model of what that might look like. Okay, so we did a Celtic Odyssey, a grand name for 25 people staying in the same house, 2 boats, and doing lots of stuff. While we were down there for the fortnight, we did surveys, we talked to people on the coastline and got their opinion. We did lots of surveying, 3 different types of boat. There's me talking to industry. We invited some people down and got them wet, and we did a benefit gig. Well, Miles did a benefit gig for the lifeboat as well while we were down there. So it was a good couple of weeks building the team together and getting some really good data, which we're still analysing. So that's a really exciting way to do collaborative fieldwork as different descriptions. Things like measuring what the flow is like. This is the flow pattern behind those rocks that we saw. The Bitches rocks are behind this side providing shadow, and all the flow comes around on the other side. So really detailed information about what that flow is doing. We're looking at it over time as well, so this is the energy in that channel as you go from ebb to flood tide and across slack water as well. What's going on? Where are the highest points of flow? Where do you want to capture flow from with an underwater turbine device? Okay, let's talk about some maths. Blade element momentum theory models. This is what happens if you don't do it properly. You get fatigue failure. So blade element momentum theory is a really useful thing to do with MATLAB. So when you complain to Dr. Evans at the back, why am I learning MATLAB? It's because you can do stuff that stops that happening. So we're developing fluid mechanics models for turbines in turbulence as a tool to help designers. Those are the equations. And that bit you can code in about 20 lines of MATLAB. Okay, so it's a quite neat, short, little model. It's taken us about 9 years to get it right, to such a point that we can do things like put turbulence through it. The dotted line is what you get with a nice steady flow, which we know doesn't exist, and all the dots are representations with different turbulent parameters and turbulent representations within that flow. So we're looking at, it's not a great graph right now, looking at what happens with turbulence. Then we add some dynamics, and from dynamics you can get variable flow, variable loadings, and from variable loadings you go into frequency domain, and from there you can go towards fatigue models. Okay, so that should tie in some of the other things you've been learning about. So from this lot, which you get from running that model in real time and then converting to frequency, you can then do things like work out your fatigue life of your turbine and try not to get the problem we saw earlier with the windmill. Then we can add waves. So there's a representation of a wave, medium, relatively deep ocean wave system. This has taken us 8 years to do. I'm quite proud of that graph. So a chap called Baltrop used the Strathclyde flume. They put a wave climber inside this 80-metre long tank and then towed a turbine through it and looked at the response of the turbine rotor to that combined wave current climate. This is their experiment. This is axial thrust and torque on the rotor blade that they saw in the experiment. And it's quite non-linear. We're dealing with aerofoil sections here, so you get dynamic stall effects, you get changes in lift over drag, so you're going to get some quite non-linear effects. So this is what they recorded in their experiment. And this is what's taken us 3 PhD students to produce a model of. And Hannah is currently writing that up to send to Renewable Energy or maybe Journal of Fluids. I'm pleased with that result. It has taken us a long time. Okay, so that's just looking at rotors and approximating the flow. Let's see if we can add the flow as well. Can we get flow and rotors and look at the interactions between them? So this is another model, a combination of the two. We have a representation of a rotor, we have some flow coming in, and some swirl at the back of the rotor behind it. So this is a relatively low speed, incompressible fluid, which is water, looking at flow models. The next talk's going to give you a completely different set of flow patterns, but it gets similar sort of nice coloured pictures. Okay, and there's more than one way to do this, and one of the arguments that fluid modelling people have is my model's better than your model, but the counter argument is, yeah, but my model's quicker than your model. And so that's something we're doing. It's a very grown-up debate, but it kind of works like this. So our colleagues at Cardiff are using fluid, and they're doing a model with a direct representation of the rotor blades here. And this is this very complex flow patterns you get from that. Our approach, we average the rotor, but still keep all of its fluid properties. So if we can do that, you can get a significantly quicker approach than solving the same problem. And one of the things we're trying to do is compare the two methods as to can we get comparable levels of accuracy but at lower levels of computational cost. If you can do that lower levels of computational cost, you can afford to do models of quite big patches of water. If these rotors are 10 metres in diameter, and we've got 1, 2, 3 of them, that ends up a kilometre long flow model. So how do we, can we do that? Is that conceivable? And from 3 rotors, we're already talking about 10 megawatt farms, 20 megawatt, 30 megawatt farms. So you might be looking at 10, 20, 30 rotors. And that's a lot of compute power if you can try and model that using this type of approach. So you need to find these intelligent ways of doing it. In theory, you see computational fluid dynamics, or BELCFD, as a way of doing this model. You write a mesh, finite element mesh, looks a bit like that. This one's structured, but it doesn't have to be. And out of that we get things like turbulence for different rotors. Here the front pair are spaced quite close together, so you get lots of turbulence impact on the back one. And here they're slightly further apart. And the same for velocity, and about how those velocity fields interact with each other downstream of the rotor. As engineers, what we're actually interested in what is the power output differences. So here we've got plots of spacing against the amount of power you get from the rear turbine. This one is clearly in the shadow, the other ones are less so. Each dot on that graph represents about 12 hours of computing on about 30 processes. Okay, so as well as just looking at computational stuff, we're trying also to understand noise. This is a plot of noise at different states of the tide within Ramsey Sound. And these two guys, you might have seen them around, spent 2 whole days on this boat, where what you do is you drive to one end of Ramsey Sound, you turn the engines off, you switch the microphone on, you record sound as you gently drift to the other end. Turn the engines back on, drive back up and drift. And they did that for 12 hours. There's a day's worth of work, up and down the channel, measuring the sound in the water and trying to work out what to do with it. Once the device is installed, they're going to go back and do it again and see the differences with and without turbine. We also play this chap called Malcolm. He sits on a rock. He's been there for 3 years already. Sat on a rock, looking at Ramsey Sound, watching the harbour porpoise, to give us a really clear picture of what's going on with the wildlife, so that when we do this bit of engineering, we can then see the differences, if possible, if there are differences of behaviour and interaction once you put devices in the water. Really valuable science. And then our colleagues across in this College of Science and Marine Biology are looking for fish. These are echo sounder outputs. Most of this is the bottom of the sea. That there is a fish of some description. Some of these here. So by doing some image processing, by doing some acoustic processing, we can identify that there are fish, and hopefully we can then carry on and identify what type of fish there are to help us with, again, conservation issues. Okay, so marine energy will power our homes in the future. The predictions are maybe 5% of UK electricity from wave, 5% from tidal stream, and 5% from a tidal barrage if it ever gets built. It's an exciting sector to be in, and we're doing some exciting research at the start of something new. So, thank you for listening.